I'm not going to be telling you guys how to deal with your own applications. I'm going to be telling you about all the other software around you that should scare the hell out of you. How many have noticed the little problem with this submarine? It's got a design problem. It's got a screen door in the conning tower. How many wish your software errors were that obvious? So we got a real problem in the world these days. No matter how much you focus on what your system is, maybe even your company, you got a problem in that you're still attackable because those you depend on, interact with, either through a supply chain or through your work, flow, they make you susceptible to attack. So the concept that I want to really get across is the idea that you need assurance about their ability to do their role in your life. And guess what? They need it from you. And so one of the things they're going to be talking about is those standardized terms and terminologies, standardized ways of expressing what you've done, what you haven't done, because we really need a better way of communicating about assurance activities so that people can, easily ask, get an answer, and move on and do the business rather than getting tied up in security reviews, safety reviews, and all the other things we deal with. So how do we get to where we are? I mean, there's software in everything these days. You actually see some demos of software in things that are very small. So I want to give you a little story. I'm going to start with my first car. It was almost a VW Bug, but the floor was rotted out, so that one went back to the dealer. And I ended up with a Chevy Vega. The only software in that car was me. There was no electronics. Any errors obviously came from me. There was a mechanical linkage between what your foot did and the throttle moving the intake on the carburetor. Now you've got a sensor that's communicating into electronics. There's software that sends stuff over a bus. There's software that interprets that and hopefully sends the right commands, and you accelerate. Well, at the same time, back then, every vehicle had a wiring harness, very specific to that vehicle and the options on the vehicle. So it was custom built, had to be shipped, and they had to make sure they had the right ones and the right number and the right plans. They learned that, hey, if we put these on a bus, we can just, send wire and some components, and we don't have to worry about that. Trouble is, they brought in that. Software and microelectronics. They didn't plan on it. They didn't say, hey, we can add software to our car. They said, we have a problem. We have weighty wires, a real hard configuration management supply chain problem. This solves it. Gives a lot of flexibility. Well, so now you have a car like this, or close to this. Even your catalytic converter is going to be driven by software as they try to optimize and get it up to temperature so your emissions are lower all the time versus when you get up to temperature. Your headlights. Today, many vehicles, the cameras that are watching the front actually are steering your headlights. In the future, if MIT is successful, you'll actually have headlights that are little beams of shaped light, and the sensors will see eyes and headlights and turn off that beam. It'll be high beam unless it's off. And there's going to be a lot of software doing that. So, and it's all networked. It's connected together, communicating. In fact, there's a lot of networks on our vehicles, and if you believe some people, there's going to be even more. If you believe some other people, it's going to be one network. I'm not sure which one scares me more. A lot of software on a vehicle these days. How many people have perfect software that's never needed an update? until they ask for a new feature, right? So there's going to have to be, how do you manage that? How do you get updates? When do you do it? Do you do it when it's in the garage, or when it's at a stoplight, or when you're 80 miles an hour on the road? Somebody's going to make that decision. So your car is also connected. It's not just a car. It's talking to sensors in the road, talking to other vehicles, talking to the street lights, lots of different things, which is not just happening in vehicles. Aeronautics, shipping, manufacturing, buildings, connected medical, all these industries are having the same influences, different versions of the same story, and it's also in our military and our critical infrastructure. So software and software-enabled and connected devices are everywhere, and it's not all written in Ada. So it's a lot of things that are unreliable is a kind word, built by people that maybe have a degree in poetry. So the trouble is, we're not just dealing with IT risks of the old. And there's a lot of managers, a lot of people in control of how this software-based stuff gets out and maintained that weren't schooled in, well, a failure could leave half the county uninhabitable. They're just not built for that kind of decision-making. They don't think of the issues. So when we come to thinking about risks, what I offer is, rather than trying to put everything into one big round risk bucket and putting a dollar value on it, let's think about where the risks are coming from. And there's a lot of different kinds of risks. So if you have specific behaviors your system has to uphold because of legal requirements, norms of an industry, or just by the nature of it, that it's very safety critical or reliability. You know, when you get into aeronautics, reliability is a big thing. You don't want things dropping out of the air. So that kind of, focus is very helpful, because really, yes, you can put a dollar value on all these things, but you'll probably get some distorted decision making and end up in court, or worse, somebody killed. So it's minding that difference between what your objective is and what you're actually able to deliver. So I'll offer one thing. A lot of people think of software as this magical thing, and they think of software quality issues as just this bland, canvas of things. I think of it as two different categories. There's software that's trying to accomplish one of those behaviors. So security features, safety features, reliability, maybe your architectures for reliability. And so that kind of software could have flaws that undermine those behaviors. But then there's the software that's just doing the functionality. If it has some of those errors, you could also undermine these behaviors. So don't get fixated. I've seen people do a security review, quote unquote, and all they did is look at the security features and its implementation, and they had all kinds of errors in the other logic, and it just undermined the whole system. So don't let people do that. In the Industrial Internet Consortium, we've actually come up with this diagram to kind of represent all these concerns. So you've got your privacy, security, reliability, resilience, and safety. Those aren't going to be the same for every application, every system. And so those rings aren't set. Some may be smaller, some, exactly their position relative to each other. And that's why they're set in this trustworthiness ring. If I asked any one of you to go down to the curb and get a trustworthy cab, and while you're walking down there, think about what a trustworthy nuclear control system would be, you're not going to have any problem with those two uses of the word trustworthy. You understand it's a contextual. One of them, you'll be more rigorous, you want more evidence to support it. The other one, you'll be a little looser. So trustworthiness lets us say, hey, depending on the system, what it's doing, its context, its hazards, the implication of failure, you may have different things you need to look at and different levels of rigor in what you need to get confidence or convey confidence to someone else. The other part of this is, if you look at people who have done safety and reliability, security, they've dealt with 1, 2, or 3 of those different external influences, whether it's a mistake by a human, an attacker, a system fault, or an environmental disruption, but most of them have not had to deal with all of them. And yet in these kinds of connected, out in the world physical systems, you do. And so it's to remind them that they need to consider all those avenues of impact to a system. So how do I get enough? Even if I was able to figure out what enough is, we think of it as, again, kind of separating that out. We do have different sets of requirements, but what are those requirements? Well, your first predilection may be, oh, there's specs out there, our standards. I can grab those and apply them. Please don't. They're probably totally inappropriate for your system. They may have a lot of good ideas for what you would want, but don't try to apply them all, because they were built for those specs were for specific situations in specific areas. What we really want to make sure is you pick out the things that are appropriate, that are testable, verifiable, and then you balance that and you keep a focus on that composite. If you have teams that are your safety team, your security team, you're going to have to get them to work together, because I have yet to see a system that has a switch. Oh, I'm in safe mode. I'm in secure mode. I'm in reliable mode. No, it's a system that works. And the question is it going to work with the right mixture of those behaviors? So about 1999, MITRE started a journey with many people in the industry on dealing with software. So that took us from, and I'm going to go into these in a little depth, but it took us from CVE, took us to CVSS, a community standard for how do you prioritize. CWE, what is it that went wrong in the first place? CWSS, how do you prioritize those? And then, of course, the thing that makes all these make sense, the attacks. If you don't understand how your systems are being attacked, you're really fighting with a blindfold and one arm tied behind you. Because understanding the attacks, understanding how they influence your system, how they find these vulnerabilities, really can help you understand where to focus your energy, whether it's at the architecture level, at the coding level, at the implementation level, because you have many levers and knobs that you can use. So we're going to walk through these. So CVE, back when we started CVE, the world had software, it was out there, it was working. You got alerts, you got incident reporting, you got priority lists, scanning tools, intrusion detection tools. There were researchers, websites, and of course the vendors. Trouble was that they all called vulnerabilities by different names. The norm back then was you would kind of catalog them along its behavior or its characteristics, and then give it a name or a number. So when you got 2 reports, you didn't really know if they were talking about the same thing. In fact, that's exactly what happened at MITRE. My colleague, Steve Christie, he was being asked to get a new network vulnerability scanning tool. And we had one, and they wanted to get a new one. And they were looking at 2 of them, and it was very confusing because one talked about the 100 or so vulnerabilities it scanned for, and the other one looked for 900. And yet nothing in the knowledge bases matched. And that's just ludicrous, because you have the same software that's being scanned. How could they not be talking about the same things? Same time, another of my colleagues, Dave Mann, he was being asked, we got this alert from CERT CC. Are we susceptible to it? And he couldn't figure out, because that name that the cert used had nothing to do with our current scanning tool. And so he couldn't tell if we were susceptible to this or not. Luckily, Dave was a bike enthusiast, and he was down in the athletic center at MITRE on a stationary bike, and he happened to be reading a Scientific American article. And in that article, it was talking about the periodic table. And it turned out that the periodic table was in existence, was preceded for 200 years by the list of elements. And his aha moment was, everybody's trying to talk in terms of periodic tables, and they haven't even agreed on what the basic elements are. We're not even talking about the same things. So we basically came back and offered up CVE to the community in a research conference. It was taken up very strongly by the attendees and government, industry. Academics went to a couple other sessions, and then they realized that they were only talking to themselves, and they came over to our session. But basically, it's very simple. It's an ID. It's a very flat namespace. It's a short definition. If you know CWE, you'll recognize the descriptions. They didn't start out that way, because back when we started this, we didn't have CWE. So we were just characterizing the vulnerability. But once we had CWEs, we used that style to make the descriptions. Most important part is all the public references to that. So the other part of this was all the vendors started assigning CVEs and putting them in their initial advisories. So the moment there was any public information, you already had the CVE ID. And guess what? The tool vendors said, oh. So when they told their tool how to find that thing, there was the CVE ID. And pretty soon, every source of knowledge had the CVE ID associated with it. And guess what? You could correlate all of these sources of information. So that's basically what CVE became. And what the team of us doing it said, well, we were looking at all of these CVEs and we were tracking them and trying to figure out what's going on. Turns out it was mostly, depending what the researcher, security guy decided to look for when he got up in the morning. There was just plenty of bugs to be found, right? But when you talk about it at this level, it's very useful operationally if you're trying to decide to apply a patch, but it's not so great if you're the developer trying to avoid these. It's just way too macro. But we were looking at trends, and the trends were going asymptotically up. And it occurred to us that none of us who knew software had ever been trained about these, taught about these, to avoid these. And so that is why we created CWE. So if you're trying to get rid of a cross-site scripting or avoid it in the first place, well, there's 9 different kinds, depending on which language, what resources you're using. Same thing with buffer overflows, directory traversal mistakes. So that's what CWE is. It's basically a compendium, and you can print it out or you can look at it on the website. Very nice table of contents. We actually did this because a little company in north area that makes a lot of software, they accused us of breaking their browser. Turns out that they were printing out CWE off the website, and it broke all the browsers. And so we basically went in and made a style sheet that took our knowledge base and created this PDF. So that if you wanted to read it as something, you can. It's got the names of the CWEs on the side of the page, so you can flip through it easily. It's got index. So if you want that, you can make use of it. Most people end up just following the link found in their tool findings to discover what the tool is talking about. But the other part of this is the attacks. So KPEC was, how do people attack? I'm a person who really wants to understand, you got this defect, okay, so what can you do with it? I guess I wasn't imaginative enough. But attack patterns show how the attacker finds that and how they leverage it and what they can do with it. So just an example, SQL injection flaws. Anybody know about those? So this is how they find them and attack them. You know, you basically have some app, let's say it's a web form, and there's some kind of a database application behind it. And so if I put a single quote in all the forms on that and submit it, and I get an error message from the database, I've talked directly to the database. No arbitration of it. So somewhere there's a SQL select that's talking and it's getting user input directly. So that's great. So now all I have to do is figure out which form, and when I do on that particular version of Microsoft SQL, I could actually then give commands at the system level. I'll own your password table in a couple of minutes, and I now own your box just through a SQL error. A lot of people say, well, I'll just turn off errors so that no errors will happen. Well, that's called blind SQL injection, and it may take them 2 minutes longer, but they'll still get in. So that's KPEX 66. So I happened to be in Japan many years ago, and I was at a place that monitored networks. And these are all the alerts for SQL injection attacks. This is US, that was Europe, Asia, sorry. And I noted, wow, you guys don't have as big a problem here. And they said, oh, sorry, we had Beijing off. So the thing is, you don't have to be a big, juicy target to get attacked for application level attacks. There's bots and things just scanning out there for you. So don't think, oh, I'm a little small company, I don't have to worry about that. So these are available, lots of different patterns. So the other part of this is, okay, do I just run a bunch of tools? I run one tool. Well, actually, you ought to think about that. Different tools, just like in a shop, you have different tools for different jobs, different types of testing techniques, find different things. So we put together CWSS so that you can focus on figuring out which weaknesses you care about and then lining up tools and techniques that actually can find and give you assurance that you've actually addressed those. So if you had all of CWE, you know, there's 700 of them, about to be 900. You know, which ones really do I care about for a particular application? So that's what you really want to do. And so we've got, thanks to the OWASP Foundation, this model where you got the attackers, and I also sometimes think of it as the threats and hazards. They're going to come through some technique, but they're only going to be able to come through weaknesses. Now, the weaknesses can be at your architecture level, your design, the way you coded it, or the way it was deployed. Any of those could be the opening. But the question is, how can I keep them away from the assets and functions so they have no impact on the thing's business function? And that's where the countermeasures and actions. Now, a lot of people think of mitigations as things you put in place in the system, but I think of them as things you do in the life cycle. So you can do a static analysis, you can do a code review, you can do an attack surface analysis, you can do fuzzing, any of these techniques. Yes, you could put a firewall in too, but there's a whole slew of things you can do. And what you need to understand is that in CWE, there's only these 8 impacts. So if a weakness shows up in your application and it's exploited, one of these 8 things is going to happen. And the question is, given that application and what it's doing for you, how do you rate these? Give them a weight of 0 to 10 across these, and CWSS will roll that up and actually allow you to, so that vignette, that little story is what I was talking about. So you'll end up with your own list, weighted list of which weaknesses. And then you can line up and figure out of that, what am I going to do to find and remediate each of those. So this looks a little bit like CVSS. There's a base score, which is the nature of the beast, the weakness. There's a attack surface group, which in CVSS, that's kind of your temporal, what's the attack environment look like? And then the environmental group is more your organizational, what have you been doing to mitigate it? What are things particular? And that business impact part is how you tailor it to the application and what its failure modes mean. And what we have is CWSS has this risk analysis framework inside it for dealing with that called CRAF. It's a silent W. I couldn't figure out how to pronounce a W. So we've actually brought that and standardized it. So this is not a MITRE standard. This is not a US standard. This is international standard. So you can ask from any of your suppliers or be asked by anyone. It's a valid international standard. In fact, all of these things are international standards. We brought them all to ITU, which is, there's IEC, ISO, and ITU. Those are the three national standards bodies where countries vote on things, not companies. And so it basically defined the space. So, there may be others who come up with different ways of conceiving of software issues, but they'll never become standards because they can't violate the existing standards. So that was a thing we did back in 2010-ish time frame, so that we could have an industry that had standards, stabilized concepts, and researchers love this, very enthused on it. I want to talk about one other thing. So far I've talked pretty much about security when I got into the code, yet I started out talking about safety and reliability and these other concepts. So another effort I've been involved in is the Consortium for IT Software Quality, CISQ. And we basically went and came up with 4 areas of quality that we were going to standardize. When I say standardize here, I mean if it's basically a level of, if these are in the code, I will not accept the code. So these aren't things that tend to, oh, it's a false positive, I've got other things that are preventing it. These are things that, if it's there, I don't want it there. But it's not just in security, it's in performance, maintainability, and reliability as well. And so those efforts, here's some examples, it kind of fits in the ISO standards about quality. So the one about security, which is based on CWES, and then there's others. So they actually had no enumeration to kind of organize those areas. So we came up with something called the Common Quality Enumeration. I think of this as a 3-year research project that got 2 years of funding. We put it out there about 1.5 years ago, and it was well received by the researchers. A lot of vendors looked at it and said, oh, this helps me map a lot of my findings that weren't security relevant. And what I can tell you is that we're actually rolling that into CWE. So in about 2 weeks or so, CWE is going to have about 190 new entries that are reliability, performance, and maintainability focused. Now, quite often, those are just as big a concern to an enterprise as some of the security issues. So this will help balance some of that. So this will be coming out very soon. The other part we talked about was assurance. How do I communicate? How do I actually convince somebody that I may not have met yet that I've done the right things? So I'll offer assurance cases or safety cases as really something that could be used. Now, historically, these have been kind of an organized way of putting your diary together of a project so that you can show somebody. But what happened about 6 months ago is that OMG, the Object Management Group, passed a standard for exchanging assurance cases. So it's basically a file structure for import or output of an assurance case. And it basically will let you exchange very complicated assurance cases and it be input in, and consumed and understood. The real value, while this, helps you organize your thinking, what are you claiming, why do you think it's true, what's the evidence to support it? The real use is in the kind of case here where you can actually decompose assurance cases or turn it around, you can compose assurance cases. So if you've gone and totally proven, given evidence, got real good sound reasoning about this is safe, secure, reliable, under the following conditions. And that's the part that people don't tend to do. Document what are your assumptions, what are your prerequisites. But if you do that, and then show that the system it's becoming a component of can fulfill those requirements, now you have composability. And that will dramatically simplify the way we think of systems, and it also will open up an ecosystem of components. Because I can actually do my engineering, do my assessment of a component, whether it's an actual board with software on it or just a module of software, and really do the analysis, put out what exactly my assumptions and prerequisites are, and now you can shop around and find things that you can actually compose into an assured and safe system. So, moving back, that little chip, microelectronics, and the software that's on it, we don't do a good job of keeping track of what our systems are running on. And it matters, especially when you get into the industrial IoT systems, where, okay, I've got a chip. Well, how many versions of that chip have you fielded? Because if you have a different version of a chip, you have different behavior. Is that behavior relevant? I don't know. But you don't know which versions you have. So how would you ever tell? So we need to start keeping track of these things. What versions of chips, what versions of firmware, what versions of the OS, what versions of the app, what versions of the language, the compiler, the linker, the framework, because those could matter. They may not. But if you're going to have a reliable, safe, secure system, you're going to have to say, this software from this version with this compiler, with these flags, with this framework, with this linker, with this version of the firmware, and this version of the chip. And that's what I'm going to assure you about. If it changes, let me get back to you. May not matter, but it may. So a bill of materials is something I think the industry really needs, where you're explicit about what you have, what it's composed of, and since we have to deal with supply chain, I think not only do we need the bill of materials, but we need provenance and pedigree so we can actually track through the supply chain. Where did it come from? Who influenced it? Because I may need to go back and get assurance from them about something. And I don't, so that's a real threat to a lot of people because who they team with, how they put things together was seen as part of their special sauce. I think we need to get past that. We don't allow that to happen in the food supply. Why should we allow it in something that's even more life critical in many situations? So supply chain, a lot of people think of it sometimes as you optimize it and you make sure you don't have shortages. Others think of it, well, I gotta worry about counterfeits and theft. I also think of it as quality. Are you getting the right quality things? Is it managed? And so there's many different aspects, but supply chain of cyber-enabled, of software and software-enabled capabilities is becoming a bigger and bigger part. And remember, those IT guys, they don't understand some of this. They don't appreciate the risks. So really need to get people involved. And so you guys and your companies, not only do you build things, but you buy things, you integrate things. You may want to think about who's providing those and what rigor has gone into them. If you need to think about how supply chains are attacked, the KPEC catalog actually has attack patterns, not only for software, but supply chain, people, social engineering attacks. So it's there to help you, kind of inform your thinking. You don't have to start with a blank sheet of paper. So one other thing I wanted to talk about, we're here in this building. I don't think any of us thought about, oh, was this building going to fall down today? Because there's a legacy of things that have gone into giving us confidence in buildings. Now, in some other countries, maybe in a different story, but back 4,000 years ago, we had a king who said, if a building falls and kills the occupant, put the builder to death. That motivated a lot of accountability. They also have this wonderful thing called laws of physics, Boyle's law and others. Their world doesn't change when somebody updates a language, updates a library. It still behaves the same as it did yesterday. So when you architect, you've got all those years of experience. When you engineer, they've gone through learning these things as guilds, apprentices, and now licensed and certified. They've got a science behind the materials and strength of materials. What do we have in software? Well, I would offer not much. And it has nothing to do with the software. It has to do with the theories of the software and the math. When you talk about architecting, they go, is it done? You're behind schedule. When talking about engineering, and I'm using architecting and engineering very loosely, in the physical world, physical sciences, engineering, somebody who's an engineer, that's a licensed, certified position. That is not what a software engineer is. So we've got a long way to go, and given how much of our society depends on software, this is really I was going to say a shame, but that's really too light a word for what this is. So going back to this model, how do you find those weaknesses? You use tools, you use techniques. So how many notice that there's a lot of white up here? What that means is the test cases, which is each line, and the tools that we're looking at the test cases missed a lot of things. Now, they may have missed it because they were not trying to find that thing. Not all tools find everything. Or maybe they're not a very good tool, or they weren't used very well. The thing to remember is, don't just run a tool, especially if you don't know what that tool is trying to find. So when you think of all the things you could look at in a software development effort, there's a lot of artifacts you can analyze, a lot of different techniques that you can apply, but they all have specific scope. So understand that scope, knit them together so the things you care about are actually covered. Because if you're not, then you're never going to be able to have assurance yourself, never mind convey it to somebody else. So all that can be part of what you put in an assurance case. You can also put things about how you organize the project, how you had licensed people or people who did training. But the last part is going back to what I said earlier about standards. Each sector of our society depends on the other sectors. If we actually come up with a way of gaining assurance that's sector specific, we're going to have a lot of confusion, people talking past each other. So having a standard way of talking about software-based assurance and communicating it as assurance cases would really improve the way we interact. So just to get off the stage with something a little lighter, how many people are aware of the GPAC 2015-16? Okay, well, you're all going to learn a little bit. You may not want to drive your car after this, but so the buses in that vehicle, there was the management of the car and then the entertainment system. So over here, number one, that's the radio entertainment system. It's the thing that interacts with the outside world. On these, they had a link to a phone network, but often there's a USB drive key that you can use to load software. It's just the kind of model the software, the car industry has come up with. Trouble was that entertainment system was a Linux box, and it had a guessable root password. Now, you think about it, you got all these vehicles, how does it, comes into the service bay, and how do I get in to do maintenance? Do I go look up the system and get a password? Well, what they did is they put the password on your windshield. It was the VIN. It was based on the VIN of your car. So they just got in. Now they own that box. They can do whatever they want on that box. One of the things that box is wired to do is provide maintenance of the gateway that separates the two buses. But don't worry, you had to have a signed checksum on the new load to burn a new piece of software. Trouble was, it didn't check the checksum. So they were able to overwrite that. So now they can send any command they want over that bus. So if you saw the videos, and you can Google it, you can find videos. They had a reporter in there, and they basically were opening, closing windows, turning on the flashers, the windshield wipers, the radio, and moving the steering wheel, accelerator, braking, all kinds of things. Anything that's enabled. What you didn't probably notice is they were doing it all at under 5 miles an hour, because these hacks only worked in what was called diagnostic mode. So that was 2015. In 2016, the team of hackers realized that the vehicle only knew how fast it was going because the tire pressure management system told it. So it's a radio in your wheel, turning around, talking to a radio on the car. It's got a protocol. Protocol doesn't allow replay attacks. So if a message goes by, I make that message and change the payload, it'll reject it. Trouble was the structure of the message IDs was very guessable. So all they did is inject their message before the legitimate message. So they told the car it was going 4 miles an hour. The car believed it, and now all the hacks worked as they accelerated up to highway speed. So an assurance case where they were more explicit about assumptions and what they were doing and how they linked may have found this. Good engineering would have, but they didn't look at this as a software issue, as a networking issue. They were car manufacturers. They were putting together things that lightened the load, added functionality. They didn't understand the materials they were using to build the system. So hopefully in the future, when we talk about these, you're going to be bringing in hardware, software, services. What I hope you'll be doing is bringing in assured hardware, software, and services, and you'll be combining them, and you'll be able to attest how well it's going to fit the situation it's meant to run in. So a lot of things there. There's an article that captures a lot of it. It was in the Industrial Internet Consortium's Journal of Innovation, the September issue. There's also 8 other articles about trustworthiness in industrial IoT. So if you want to see something that's not just pictures, you'll recognize the pictures. So.